This is TMUA 2021, Paper 2, Question 6. We're given two statements, P and Q, about a polynomial f. P says that f of x is equal to 0 for exactly 3 values of x, and Q says the first derivative of f is equal to 0 for exactly 2 real values of x. I want to determine if P is necessary and or sufficient for Q. So let's first look at necessary. Well, what does that mean? That means if P is necessary for Q, then Q being true implies P being true. So if our polynomial has 2 stationary points, which is what Q is saying, then it has 3 roots. Okay, so does this seem true? So let's first, what could f be? F is a polynomial, so it could be of this form. an times x to the n, all the way up to plus anx, a1x plus a0, where these ai's are real. And then differentiating term by term, you get that f prime of x is n times an times x to the power of n minus 1, all the way up to plus a1, and this a0 disappears. So we're comparing the roots of these two equations, and they don't seem related as these are polynomials with different coefficients and different powers. So if this is true for all polynomials, we'd guess no. So we need to find a counterexample to this. So what does that mean? We need to find a function that satisfies Q but doesn't satisfy P. So we need one with 2 stationary points but not 3 roots. What example can you think of this? Well, 2 stationary points, that often occurs with cubics. So let's take a cubic and we want to make sure that it doesn't have 3 roots. So how might we do that? Well, you can just take a favourite cubic with 2 stationary points, and then if you just translate it up sufficiently large, you can make sure that it doesn't have 3 roots. For example, if I take x times x minus 1 times x plus 1, this is a cubic like this with the roots at minus 1, 0, 1. At the moment it has 3 roots, but then if you just translate it up sufficiently large, we can move this stationary point above the x-axis, and then it only has 1 root. So this is a counterexample to this statement. So it's not necessary. Is it sufficient? Well, that's the saying that if P is true, then Q is true. I.e., do we have a function, if it has 3 roots, does it have 2 turning points? Again, they don't seem related, so you'd say no. So what would be a counterexample for this? So we want something that has 3 roots, but not 2 stationary points. Something that's 3 roots is often a cubic. So we can, let's say, take our favourite cubic, and then we can affect the number of stationary points by just adding in a repeated root to our equation, as that doesn't affect the number of roots, but it does add in an extra turning point. So let's just take x minus 1, x plus 1, which looks like this curve here. This has 3 roots, but 2 stationary points. And then if I just make this an x squared, we've now added in an extra stationary point at x equals 0. So this graph is going to look something like this. So it's still got 3 roots, but now it has 3 turning points here, here, and here. So this is a counterexample to our statement. So it's not sufficient and it's not necessary. So the answer is D.